Before we begin, remember this. The universe you know is only one version of reality. Behind every choice, behind every quantum shift, there may be countless worlds unfolding in parallel. Today, we're exploring the most fascinating facts about the multiverse, straightforward, science-based, and told like a story unfolding across infinite possibilities. Chapter 1. The multiverse theory suggests our universe may be just one bubble among countless others, each with its own laws of physics. Some could be nearly identical to ours, while others follow rules that defy our understanding. The idea grew from cosmic inflation, which implies space didn't expand evenly. Where expansion varied, new universes may have branched off. Chapter 2. Physicist Andre Linde proposed eternal inflation, where expansion never fully stops. In this model, pockets of space stabilize and become universes. Others keep inflating endlessly, creating an infinite cosmic landscape. This means new universes might be forming right now, beyond what we can ever observe, each carrying different possibilities and outcomes. Chapter 3. Some versions of the multiverse come from quantum mechanics. The many worlds interpretation suggests every decision or event splits reality. When a particle behaves unpredictably, the universe branches, creating new paths. This implies countless versions of you exist, each shaped by different choices. It's not fantasy, it's one attempt to explain quantum uncertainty. Chapter 4. Another idea comes from string theory, which predicts tiny vibrating strings form everything in existence. String theory allows extra dimensions curled up beyond our perception. Depending on how these dimensions fold, different universes emerge. Each configuration becomes its own cosmic blueprint, producing different particles, forces, and even different forms of matter. Chapter 5. Some scientists suggest our universe's physical constants seem too precise for life to exist by chance. In a multiverse, this fine-tuning isn't mysterious. Life simply appears in universes where the conditions work. It's not special, it's statistical. We're here because our universe happens to allow atoms, chemistry, and eventually observers. Chapter 6. The observable universe has a horizon, limits defined by the speed of light and cosmic expansion. Beyond that boundary could lie regions of space forever unreachable. Some researchers say these distant zones might follow different physics. If so, our universe may be only one patch in a much larger cosmic quilt. Chapter 7. Black holes might be gateways to new universes. The theory suggests a collapsing star compresses everything into a singularity, then bounces into another cosmic region. Each black hole could seed a universe with slightly different laws. If true, our universe may have been born inside a black hole from a parent cosmos. Chapter 8. Cosmic background radiation, the afterglow of the Big Bang, contains tiny anomalies. Some scientists speculate these irregularities could hint at collisions with other universes. Though not proven, the idea remains intriguing. Our universe might bear scars from past encounters, subtle imprints left behind from cosmic neighbors brushing against us. Chapter 9. Mathematical multiverses argue that every possible mathematical structure becomes a universe. If reality follows math, then any consistent equation set could manifest as a cosmos. This means universes don't need physical causes, only mathematical possibilities. It's abstract, but it pushes the boundary of what real might mean. Chapter 10. Simulated multiverse theories suggest advanced civilizations could generate countless digital universes. If computation grows beyond imagination, entire cosmologies might be simulated with conscious beings inside them. Our universe might be one simulation among billions, each running its own rules. If so, detecting subtle glitches could reveal hints of the underlying system. Chapter 11. Some multiverse models suggest time may flow differently across universes. In one, time could run slower. In another, it might not exist as we know it. Without time, events wouldn't happen, they would simply be. This challenges our assumptions, reminding us that our experience of time might be one version among countless cosmic possibilities. Chapter 12. In certain theories, universes might collide like bubbles in a cosmic foam. When two universes touch, they could imprint circular patterns on each other's space. Researchers have searched the cosmic microwave background for such signatures, hopping to catch evidence of past collisions. No confirmation yet, but the idea keeps pushing scientists to look deeper. Chapter 13. Some universes may contain different types of particles entirely. Without familiar atoms, stars and planets would never form. Instead, matter might behave in exotic ways, stable or unstable, heavy or weightless. These strange universes could be silent, chaotic, or filled with structures we can't imagine, shaped by rules completely foreign to our physics. Chapter 14. Quantum fluctuations, tiny bursts of energy, might trigger universe formation. In the vacuum of space, brief disturbances could inflate into entirely new realities. It's like random sparks growing into full cosmic fires. If such fluctuations happen endlessly, then universe creation becomes a continuous process woven into the fabric of existence. Chapter 15. The multiverse challenges our understanding of beginning and end. If universes constantly emerge, reality might have no true start. Some theories suggest cycles. Universes expand, collapse, and give rise to new ones. This endless loop reframes the Big Bang, not as the first event, but one chapter in a repeating cosmic story. Chapter 16. If the multiverse exists, probability takes on a new meaning. Rare events, almost impossible in our universe, could be common somewhere else. Conditions that seem miraculous here might be ordinary in another cosmos. This perspective removes the need for luck, replacing it with the vast statistical reach of infinite possibilities. Chapter 17. In some models, universes may differ not only in physics but also in dimensionality. We live in 4 dimensions, 3 of space, 1 of time, but others might have 5, 6, or more. Extra dimensions could reshape gravity, motion, and even the nature of life. Such universes might be inaccessible but still mathematically consistent. Chapter 18. Cosmic strings, hypothetical ultra-thin defects in space, could connect or separate universes. If they exist, these structures might stretch across vast distances, carrying enormous energy. Some theories propose they could act as boundaries between different cosmic regions. Detecting them would open a new path to understanding how universes might interact. Chapter 19. Light behaves differently across multiverse theories. In some universes, light might not be the fastest signal. Other forces or particles could dominate, shaping entirely new kinds of physics. Without our familiar speed limit, causality itself might operate differently, allowing interactions that seem impossible within our own physical laws. Chapter 20. Entropy, the tendency toward disorder, shapes our universe's direction of time. But in some universes, entropy could behave differently. If it decreases instead of increases, time might feel reversed. Events could unfold from order to chaos in unfamiliar ways. These variations show how deeply our universe's behavior depends on its precise physical conditions. Chapter 21. Some theories propose universes with stronger or weaker gravity. If gravity were slightly stronger, stars would burn out quickly. If weaker, planets might never form. These variations show how sensitive cosmic structures are to physical constants. In the multiverse framework, such differences aren't surprising. They're part of a vast landscape of possible realities. Chapter 22. Dark energy, responsible for accelerating our universe's expansion, could vary across universes. Even tiny differences would lead to radically different outcomes. Too much dark energy, and matter never clumps into galaxies. Too little, and everything collapses quickly. Our universe sits in a narrow range that allows complexity, highlighting how rare balanced conditions might be. Chapter 23. Some cosmologists suggest quantum entanglement might extend beyond our universe. If particles remain connected even across cosmic boundaries, entanglement could form a subtle link between universes. Though speculative, it hints that reality might be more unified than we assume. Hidden connections could weave complex patterns across an unseen multiverse network. Chapter 24. Time travel theories gain new meaning in the multiverse. Instead of changing the past, travelers could shift into parallel timelines where different outcomes unfold. This avoids paradoxes by placing altered events in separate universes. While still theoretical, it offers a clean explanation for how multiple histories could coexist without contradiction. Chapter 25. Some universes might have different stages of cosmic evolution. In one, stars could ignite earlier. In another, galaxies might never stabilize. Without stable environments, life would struggle. These variations suggest that our universe's timeline is finely arranged for long-term development. Within a multiverse, it becomes one successful arrangement among countless unsuccessful ones. Chapter 26. The anthropic principle uses the multiverse to explain why our universe allows life. Rather than being uniquely designed, we exist because only universes with suitable conditions can produce observers. It's a selection effect, not a miracle. This perspective removes mystery and frames our existence as an inevitable outcome of statistical reality. Chapter 27. Some theorists propose universes where chemistry doesn't follow familiar patterns. Atoms might form unstable bonds or none at all. Without complex molecules, biology becomes impossible. These chemically barren universes show how dependent life is on subtle atomic interactions. In a multiverse, such lifeless realms could vastly outnumber hospitable ones. Chapter 28. Multiverse theory influences the search for alien life. If countless universes exist, life might arise in many forms, not just within ours. This broadens our understanding of biology, hinting that life could adapt to entirely different rules. While we can't observe other universes directly, the idea encourages new perspectives on what life could be. Chapter 29. Some models predict universes born from quantum tunneling, where energy escapes a vacuum state to form new space. This process could happen spontaneously, without a preceding universe. Each tunneling event seeds a fresh cosmic expansion. If true, reality may constantly regenerate, with universes emerging from the quantum fabric like sparks from a fire. Chapter 30. A universe with a different speed of light would behave dramatically differently. Faster light speeds could dilute gravity's influence. Slower speeds might make the universe more compact. These shifts alter the balance of forces, reshaping everything from particle interactions to galaxy formation. Such diversity fits naturally within multiverse concepts. Chapter 31. Some universes might lack electromagnetic force entirely. Without it, atoms couldn't bind, light wouldn't exist, and matter couldn't interact the way we know. Such universes would be dark, silent fields of particles with no structure. This reinforces how essential each fundamental force is for forming stars, planets, and eventually conscious observers. Chapter 32. In certain multiverse theories, universes may recycle energy differently. Our cosmos gradually cools as stars fade, but others might maintain energy through continual particle creation. If so, they could remain active far longer. This variation shows how different energy rules sculpt cosmic lifespans, influencing how long complexity has to develop. Chapter 33. Some physicists explore the idea that universes might share a common origin before diverging. In this scenario, early conditions split, sending each universe on its own trajectory with unique constants. It's like branches growing from the same trunk. The shared root hints at deeper underlying laws shaping every cosmic variation. Chapter 34. In the string theory landscape, the number of possible universes is enormous. Some estimate 10,500 variations. Each configuration represents a different vacuum state with distinct physics. This vast range isn't exaggeration. It arises naturally from the math. The sheer scale highlights how small our universe may be compared to the full set of possibilities. Chapter 35. Some models suggest universes could influence each other gravitationally. Even without direct contact, massive cosmic structures might subtly tug across dimensions. These faint interactions could leave patterns in cosmic expansion or background radiation. Though challenging to detect, such signals might offer rare clues that other universes are physically real, not just theoretical. Chapter 36. The multiverse concept reshapes how scientists approach unsolved mysteries. Instead of assuming one universe must explain everything, researchers consider broader systems with multiple environments. This allows solutions based on variation rather than precision. Problems like fine-tuning or cosmic symmetry become statistical, not singular, making complex puzzles easier to frame and study. Chapter 37. Some universes may evolve with reversed physical priorities. Gravity might be dominant while electromagnetic interactions weaken. Such environments could produce dense, fast-forming stars and unstable planetary systems. Life, if it forms, would face constant cosmic hazards. These extremes show how narrowly balanced our universe is compared to potential alternatives. Chapter 38. Quantum decoherence, the process where quantum states become classical, plays a key role in many worlds' multiverse models. Each time decoherence happens, the universe effectively branches, creating parallel outcomes. This isn't science fiction. It's a mathematical interpretation of quantum behavior. If accurate, reality constantly splits, forming a vast tree of diverging histories. Chapter 39. Some universes might never cool enough for stable matter. If background temperatures remain too high, particles wouldn't settle into atoms. Everything would remain a hot, chaotic plasma. Without cooling, stars wouldn't ignite, planets wouldn't form, and complexity couldn't rise. These universes remain forever young and turbulent, stuck in cosmic infancy. Chapter 40. In certain theories, universes might differ in symmetry. Symmetry determines how particles behave and forces interact. When symmetry breaks differently, entirely new particle families could emerge. These shifts change the building blocks of reality, shaping everything from mass to motion. It reveals how much our universe depends on delicate symmetry patterns. Chapter 41. Some universes might follow different nuclear forces. If the strong force were slightly weaker, atomic nuclei wouldn't hold together. If stronger, stars would burn violently and briefly. These delicate balances define whether elements like carbon or oxygen can exist. In a multiverse, such variations aren't rare. They're natural outcomes of countless cosmic configurations. Chapter 42. Certain theories allow universes to exist with no Big Bang at all. Instead of starting from a singular explosion, they might begin as steady, eternal expansions. Others could emerge from gradual transitions in quantum fields. These alternative beginnings show that our explosive origin might be only one version of how universes come to life. Chapter 43. Some universes may be dominated entirely by dark matter. Without ordinary atoms, they wouldn't have stars or planets, only vast halos of unseen mass shaping silent structures. Nothing would shine or reflect light. Though lifeless by our standards, these universes remind us that dark matter plays a bigger role in reality than we fully grasp. Chapter 44. In multiverse models, universes might differ in how space curves. Some could be open and infinite, others closed like spheres. The shape of space affects how galaxies form and whether expansion continues. Our universe appears nearly flat, a rare balance. In the multiverse view, this flatness might be just one outcome among many. Chapter 45. Some researchers propose universes that cycle endlessly, expanding, collapsing, then rebounding into new forms. Each cycle could reset physical constants, producing different cosmic rules every time. If true, our universe may be one phase in an infinite chain of transformations, each carrying faint echoes of the cosmic cycles before it. Chapter 46. While our universe has 3 spatial dimensions, some theories propose universes with only 2. In a 2-dimensional world, gravity would behave strangely, planets couldn't orbit, and structures would collapse. These dimensional experiments highlight why our 3-dimensional space is uniquely stable for complex matter, and how fragile the conditions for life can be. Chapter 47. Mathematical models show some universes could expand too quickly for matter to ever connect. Galaxies wouldn't form because particles drift apart before gravity binds them. Such universes remain empty, vast, and silent. These barren worlds demonstrate how expansion rates determine whether anything meaningful can emerge in a cosmic environment. Chapter 48. Some universes could be incredibly dense, with matter packed closely from the start. Gravity would dominate, compressing everything rapidly. Stars might ignite instantly and burn out in moments. Cosmic evolution would occur so fast that long-term structures never stabilize. These hyperdense universes live brief, intense lives compared to our slow, methodical cosmos. Chapter 49. In certain theories, universes might contain exotic forms of matter like tachyons, hypothetical particles that move faster than light. Such particles would make causality behave unpredictably, allowing events to influence the past. These universes would feel chaotic by our standards, but their existence reminds us that reality may permit behaviors we consider impossible. Chapter 50. Some physicists explore multiverse models where universal constants evolve over time. Instead of fixed values, forces and particle masses shift gradually as the universe grows. This dynamic reality would lead to changing chemistry, shifting stars, and evolving physical laws. It paints a picture of universes not as static systems, but as cosmic organisms. Chapter 51. Some universes might contain no quantum randomness. Instead of unpredictable particle behavior, everything would follow strict, deterministic rules. Without uncertainty, reality would unfold like a precise equation. Such universes lack the spontaneity that drives complexity in ours. This contrast shows how quantum unpredictability shapes creativity, evolution, and even consciousness in our cosmic environment. Chapter 52. In certain models, universes may exist with reversed charge distributions. Electrons might be positive, protons negative, altering how atoms form and interact. Chemistry would rearrange into unfamiliar patterns, producing materials unlike anything we know. These inverted realities demonstrate how even small changes in particle charge can reshape every structure in a universe. Chapter 53. Some theories explore universes where space expands unevenly, creating isolated regions that behave like miniature universes within larger ones. These pocket realities could follow slightly different physics while remaining connected through distant boundaries. If true, our universe might be one region inside a far bigger cosmic framework we can never fully observe. Chapter 54. In multiverse discussions, symmetry breaking plays a crucial role. When early cosmic fields shifted, different universes could have settled into different energy states. Each state defines fundamental particles and forces. This process resembles paths branching from the same origin, leading to entirely distinct outcomes based on tiny initial differences. Chapter 55. Some universes might contain additional time dimensions. With more than one direction of time, events wouldn't flow linearly. Multiple timelines could interact, loop, or diverge. Physics becomes far more complex, and causality behaves differently. While speculative, these concepts expand our understanding of what time might be beyond our single-direction experience. Chapter 56. Certain models propose universes filled with primordial black holes. If these black holes formed early and densely, they could dominate cosmic structures. Instead of galaxies built from stars, these universes would revolve around massive gravitational anchors. Their evolution would be shaped by collapse and merger, creating a darker, heavier cosmic landscape. Chapter 57. Some universes may allow stable antimatter worlds. In ours, antimatter is scarce and unstable when meeting matter. But in a universe dominated by antimatter, stars, planets, and even life could be built from antiparticles. Their chemistry would mirror ours, but with opposite charges. This idea shows how familiar structures could arise under mirrored physics. Chapter 58. A universe with stronger weak nuclear force would see rapid radioactive decay. Elements necessary for life wouldn't last long enough to build planets or organisms. Conversely, a weaker force could leave too many unstable elements lingering. These differences highlight how precisely tuned nuclear interactions must be for any form of stable complexity. Chapter 59. Some theoretical universes may lack dark energy entirely. Without cosmic acceleration, gravity would slow expansion over time. Such universes might collapse into a big crunch or stabilize into a steady state. This creates radically different cosmic destinies, reminding us that our accelerating universe is only one path among many possible outcomes. Chapter 60. In multiverse theories involving holography, entire universes might exist as projections from deeper dimensional surfaces. Our three-dimensional world could be encoded on a distant boundary. Other universes may be encoded on separate surfaces, each producing its own physical laws. This idea reshapes reality as information-driven rather than purely physical. Chapter 61. Some universes might experience different types of cosmic inflation. In ours, inflation was rapid and brief, but others could inflate slowly, producing smoother, more uniform structures. Some might inflate in multiple phases, creating layered regions with varied properties. These inflation differences could sculpt cosmic evolution in ways far beyond our familiar pattern. Chapter 62. Certain universe models allow gravity to behave repulsively instead of attractively. If gravity pushed matter apart, stars and galaxies could never form. Space would stretch endlessly, leaving nothing but isolated particles. This inversion shows how essential gravity's attractive nature is for creating stable, meaningful structures throughout our universe. Chapter 63. Some theorists propose universes that exist only briefly before dissolving back into quantum fields. These short-lived flicker universes appear spontaneously and vanish almost instantly. They never develop matter, light, or structure. Their existence highlights the dynamic nature of quantum space, where possibilities constantly emerge and fade without leaving lasting traces. Chapter 64. In certain multiverse scenarios, physical constants may drift over time. Early eras might have different gravity strengths or particle masses than later ones. This shifting landscape would alter chemistry, stellar behavior, and cosmic structure as the universe ages. Such dynamic systems contrast sharply with our stable constants, showing how delicate cosmic balance can be. Chapter 65. Some universes may contain exotic geometries, twisted, looping spaces where traveling in one direction eventually returns you to your starting point. These non-Euclidean structures could create strange cosmic pathways, allowing objects to interact in unexpected ways. They demonstrate how space itself can vary dramatically across different multiverse possibilities. Chapter 66. In certain models, universes could be born from collisions between higher dimensional brains. When brains intersect, the energy released may ignite new cosmic expansions. Our universe might be one product of such an event. This idea connects string theory with cosmology, offering a dramatic, physical explanation for universe creation beyond the Big Bang. Chapter 67. Some universes might lack star formation entirely. If their initial density is too low or cooling mechanisms fail, gas clouds never collapse into stars. Without stars, no planets form, no elements are synthesized, and no complex structures develop. These silent universes show how crucial star birth is for cosmic evolution. Chapter 68. Certain theories propose universes where entropy decreases instead of increases. Instead of trending toward disorder, such universes would naturally become more structured over time. This reversal changes how events unfold and could make time feel fundamentally different. It challenges our assumption that entropy's direction is universal across all realities. Chapter 69. Some universes might exist with different quantum vacuum states. These states determine what particles can exist and how they interact. A slight shift in vacuum energy could prevent atoms from forming or allow entirely new kinds of matter. This shows how the underlying empty space of a universe shapes everything built within it. Chapter 70. In holographic multiverse concepts, information stored on cosmic boundaries may vary between universes. Different boundary conditions would encode different physical laws, producing distinct realities. Our universe could be just one projection among many. This view helps unify quantum mechanics and gravity by treating space, matter, and time as emergent from deeper information layers. Chapter 71. Some universes might contain different versions of the periodic table. If particle masses or charges shift even slightly, elements could arrange into unfamiliar sequences. New types of atoms might form stable structures unknown to us. These alternative chemistries reveal how our familiar elements represent only one arrangement among countless possibilities in the broader multiverse. Chapter 72. In certain theories, universes may form networks, cosmic clusters connected through quantum pathways. Though not physically reachable, they could still share subtle correlations. This network model reframes the multiverse as a structured web rather than random, isolated bubbles. It suggests reality might hold patterns linking distant universes in ways we don't yet understand. Chapter 73. Some universes could have drastically different cosmic lifespans. One might collapse within seconds, another might survive trillions of years. Lifespan depends on factors like expansion rate, energy density, and the behavior of fundamental forces. These variations highlight how our universe's long stability is a rare condition that allows time for complexity to grow. Chapter 74. Certain models imagine universes dominated by radiation instead of matter. In such realms, energy would spread too quickly for particles to gather into stars or planets. The cosmos would remain bright but structureless. These radiation-heavy universes demonstrate how fragile the balance is between matter and energy for building anything enduring. Chapter 75. Some universes might generate structures unlike galaxies, perhaps vast energy sheets or filament-like clusters shaped by unfamiliar physics. Without our known forces, matter could organize into shapes with no parallel here. These speculative formations show how cosmic architecture could vary wildly depending on fundamental laws. Chapter 76. In multiverse discussions, vacuum decay remains a significant concept. A shift to a lower energy vacuum state could create a new universe with different laws. This transition might spread like a bubble through space. While unlikely in our universe's lifetime, the idea underscores how reality might change abruptly under certain quantum conditions. Chapter 77. Some universes could experience extreme asymmetry between matter and antimatter. In ours, matter dominates. Elsewhere, antimatter might prevail entirely. These antimatter universes would form their own stars, galaxies, and potential life based on reversed particle structures. Despite the differences, they could mirror our cosmic evolution in surprising ways. Chapter 78. In certain models, universes might begin with far more dimensions than they end with. As they cool and expand, some dimensions could compactify, leaving only a few large ones behind. This process might determine which physical laws remain active. Our three-dimensional space might be the result of such dimensional transitions. Chapter 79. Some universes may contain no cosmic microwave background. Without this relic radiation, they wouldn't carry a visible imprint of their origin. Scientists rely heavily on this background to study cosmic history, so a universe without it would be far more mysterious. Its evolution might follow a path unlike any we can infer. Chapter 80. Certain theories propose universes where information behaves differently. Instead of being conserved, it might decay or duplicate over time. This change would alter quantum processes, computation, and even the stability of physical laws. These possibilities show how deeply information theory intertwines with the fabric of reality across multiverse models. Chapter 81. Some universes may follow entirely different rules for particle spin. If spin behaved differently, atoms wouldn't orbit or bind the same way. Chemistry could reorganize into unfamiliar patterns, forming materials with no parallel in our world. These spin variations show how deeply quantum properties shape the structure and behavior of everything around us. Chapter 82. In certain multiverse models, universes might never experience cosmic cooling. If temperatures remain too high, particles stay energetic and unstable. Atoms wouldn't settle, stars wouldn't ignite, and matter wouldn't form durable structures. These eternally hot universes remain in a constant state of motion, unable to evolve into complex, long-lived systems. Chapter 83. Some theories describe universes where symmetry is preserved rather than broken. Without symmetry breaking, particles would lack mass, forces wouldn't differentiate, and structure couldn't form. Such universes would be smooth, featureless expanses with no separation of matter or energy. This highlights how broken symmetry is essential for diversity and complexity. Chapter 84. Certain models propose universes where quantum tunneling occurs far more frequently. Particles could shift positions unpredictably, destabilizing atoms and molecules. Chemical bonds might form briefly before dissolving. These chaotic environments would challenge any attempt at structure, illustrating how finely balanced quantum behavior is in our own universe. Chapter 85. Some universes might operate with altered thermodynamic laws. If heat didn't flow from warm to cool regions, energy distribution would behave unpredictably. Systems couldn't reach equilibrium, and natural processes like star formation or planetary cooling would fail. These variations show how thermodynamics quietly supports stability in our cosmic environment. Chapter 86. In certain multiverse scenarios, universes could be dominated by massive neutrino-like particles. These particles rarely interact, so matter would remain diffuse and unable to clump into stars or galaxies. The result is a dim, ghost-like cosmos where structure never consolidates. It demonstrates how particle properties determine whether complexity can emerge. Chapter 87. Some universes might undergo rapid phase transitions early in their history. These shifts could freeze areas of space into different energy states, creating patchwork regions with distinct physical laws. Each zone might behave like a small universe within a larger one. This idea reveals how early conditions shape long-term cosmic identity. Chapter 88. Certain theories imagine universes filled with exotic fluids, fields that flow through space and influence expansion. These fluids could speed or slow cosmic growth depending on their properties. If present, they would redefine how gravity and energy interact, offering alternate explanations for cosmic evolution across the multiverse landscape. Chapter 89. Some universes may form without any baryonic matter, the type that builds atoms. Without baryons, no stars, no planets, and no recognizable elements could exist. These universes would be shaped entirely by other forms of mass or energy, representing realities built from building blocks completely different from our own. Chapter 90. In certain models, universes might follow different logic for quantum measurement. Instead of collapsing to one outcome, states could evolve in unfamiliar patterns, shaping a reality unlike the branching structure we expect. These alternate quantum rules would change everything from particle interactions to the emergence of stability, creating cosmoses that operate on unfamiliar principles. Chapter 91. Some theories suggest the multiverse behaves like a giant computational grid, where every particle is a bit of coded information. If true, the laws of physics might be the software rules of our universe. Each parallel universe runs the same engine, but executes different outcomes. It reframes reality not as chaos, but structured possibility. Chapter 92. Quantum fields could allow universes to interact through tiny fluctuations, producing rare resonance events. These interactions wouldn't create portals, but subtle physical anomalies, random bursts of energy or unexplained patterns in cosmic radiation. Scientists study these hints because they may be the faint fingerprints of neighboring universes brushing against ours, like distant waves touching the same shore. Chapter 93. In some multiverse models, time is not universal. It resets with each new universe. One cosmos might age rapidly while another barely begins. This makes before and after meaningless on a multiversal scale. Time becomes a local feature, not a universal constant, further challenging our sense of direction and sequence across reality. Chapter 94. Some universes may never form stable atoms. Without balanced forces, electrons drift or collapse instantly. These barren realities stay dark and structureless, existing only as brief quantum ripples. The rarity of universes conducive to matter makes our cosmos fine-tuned compared to countless unstable worlds that appear and vanish in the background of creation. Chapter 95. Cosmic expansion speed varies per universe. A universe expanding too fast spreads matter too thin for stars, too slow, and everything collapses prematurely. Our universe sits within a narrow, life-permitting range. In the multiverse context, this balance isn't miraculous, it's statistical. With infinite attempts, at least one universe lands in the life-friendly zone. Chapter 96. Some universes might follow exotic geometries, twisted space where straight lines loop back or distances behave unpredictably. Travelers could return to their starting point without turning. Such geometries emerge naturally in certain inflation models. Though unimaginable here, they illustrate how spatial rules aren't fixed but customizable parameters within the multiverse landscape. Chapter 97. Dark matter might differ drastically across universes. In some, dark matter could interact more strongly, shaping galaxies into tighter clusters. In others, it may barely exist. These variations reshape cosmic architecture entirely. Studying our dark matter distribution helps scientists compare models and imagine how other universes might look under alternate gravitational recipes. Chapter 98. If universes bud off from parent universes, each inherits slightly altered physical constants. This branching resembles evolutionary drift, where variations accumulate over countless generations. Instead of biological traits, it's cosmic laws that mutate. The multiverse may be a vast ancestry tree, with our universe as one leaf among endless lineage branches stretching backward eternally. Chapter 99. Some multiverse frameworks predict universes where quantum uncertainty is amplified. Randomness dominates everything, from particle behavior to large-scale cosmic events. Such universes would feel chaotic, lacking stable patterns required for complex structures. Our relatively predictable quantum landscape shows how mild uncertainty might be a rare outcome in an otherwise wildly probabilistic multiversal domain. Chapter 100. The multiverse, if real, reframes existence as an infinite experiment where every physical rule, outcome, and possibility is tested somewhere. Our universe becomes one successful configuration among countless variations. Instead of diminishing our significance, it highlights how extraordinary our cosmic conditions are, a tiny but meaningful chapter written into an endless library of realities. The multiverse remains unproven, but the possibilities it offers expand our imagination far beyond one reality. Whether these worlds exist or not, exploring them sharpens our curiosity and reminds us how rare and remarkable our universe truly is. Thanks for listening. Until next time, stay curious.